So I am Anirudhan, okay. Welcome to all of you. Basically, I am a chemistry man, okay, chemist. So that my job is to fabricate materials for day-to-day life applications, especially to improve our quality of the life. So basically, as a chemist, I prepared, especially, this is a teamwork, not from myself. We have a good group of research scholars. So everything is contributed coming from this department is nothing but teamwork, individual responsibility and teamwork. So my students are very hardworking and they work around the clock. So that we published many papers in international journal with a high impact factor. So basically, we have prepared many hundreds of materials for wide application, especially for analytical, environmental, and biological applications. So we have prepared large number of materials, especially from naturally available material, eco-friendly material, just to modify that material for a application. So now today I want to present some of the slides, especially material applicable to biomedical applications. So my topic is, today's topic is reactive functional graft copolymers for biomedical application. Of course, materials are prepared for other applications, but we have no time to present all these applications. So today I confine to these biomedical applications. And of course, this topic is also comes under this material science and engineering. And this material science and engineering involve three major activities. What are these activities? The study of the structure, properties, and behavior of the newly developed materials. And of course, these materials are developed from process industries, especially this different method that we have technologies for manufacturing of these useful products. Then, of course, we want to make utilize after application, regenerate these materials. So research is also going to recycling and environmentally friendly disposal. Disposal of the already used material. Spent material is also a challenging problem that we have. So usually these material science and engineering involve the study of recycling and environmentally friendly disposal of this already spent material. And so we have two groups of people working in this area. And these groups are material scientists and material engineers. And of course, their role is also different. Material scientists, they test the mechanical, physical, chemical, and electrical and optical properties of the material already developed in their lab. And of course, explore how these properties depends on the microstructures. Because each application, we need a material with the specific properties. So application is totally depends on the properties of the material. So we chemist people or scientists to make utilize these properties, or properties may be introduced in this particular material, so that particular material may be applicable to various fields or various spheres. Now, material engineers, once chemists prepared this material, and these engineers, of course, they make utilize their knowledge or information or understanding to select the most appropriate material and manufacturing process for any given applications. And of course, they find some drawbacks maybe after selecting, but they themselves sometimes modify. There are engineers with some chemistry knowledge. Of course, after finding some limitations or identifying the problems, they themselves try to modify already available material in the market for future applications. Now, of course, we will make our life safer, more convenient, more enjoyable, and more sustainable. So, of course, for that, we want to develop new products, materials, especially through innovative technologies. So, for that purpose, we must understand how to develop new materials that will meet the demands of the future. Now, of course, materials are important, especially in the development of civilization. You know this way, our ages associated with materials. you know this, in the origin of human life on the earth, people make utilize materials like stone, clay, skin, wood for their shelter and catching the prey during that period. So that age is known as Stone Age, and here stone is a material. So that age is associated with the name is named as after the use of the material stone. Then 3000 BC started about 3000 BC, Bronze Age. During that period, people know how to make this copper into an alloy after introducing some other metals, especially tin. When tin mixed with copper, copper becomes stronger, and they make utilize this bronze at that period for manufacture for their construction of shelters, and that age is known as Bronze Age. So what I have concluded is each age may be named as a material which they make during that period. After that, we have 1200 BC. We have iron. We have introduced iron, a stronger material that gives advantages in especially wars. They make utilize this material for manufacturing weapons and other type of tools. Then again, when iron is mixed with carbon material, of course that material become a stainless steel, and we have utilize this stainless steel, especially during 1850. That age is known as Steel Age, because people utilize this steel for construction of building and other infrastructure, especially of the industrial base, because industrial revolution is coming during that period. And now we exist in polymer age. Now we are all living in the world of polymers, especially polymer composite and hybrid material, because everything is polymer as such is not suitable for making product. So we introduce some other materials along with these polymers, and that material is nowadays known as hybrid materials or nano composite material, especially polymer mixed with metal, ceramics, glass, and other type of fillers, so that our material is categorized as a hybrid material, because this hybrid material having a new phase associated with the new phase and new properties compared with the individual properties of the material before manufacturing. Now, this of course, in order to study this material, we have many millions of materials available all over the world. So study and categorization of these lakhs and lakhs of millions and millions of material. According to my knowledge, we have 65 million different types of material available for different applications. So classification itself is very difficult. So all this material, how to classify? In general, these materials are classified as a mineral-based material, then petroleum-based material. So metals, semiconductors, and ceramics, we already know that these materials are come under these mineral-based materials. Metals, example, magnesium, aluminum, gold, and osmium, platinum, iridium are all categorized as a metal. Why metals? So especially this, after detaching valence electrons from the atom, all these valence electrons are spreaded in an electron sea, which act as a glue to bind all these ions together, is known as metals. Okay, this is what definition of metals. We have, of course, metalloids are there, but you just differentiate this metal from metalloids. So another group of mineral-based material is semiconductors. There you have we have atoms where electrons may be shared. Two atoms share themselves with their own common electrons. So and form a covalent bond. So semiconductors always associated with the sharing of electrons from the atoms and form a strong covalent bonds. And of course, one of the most important property of the semiconductor is nothing but opaque and to visible light, but transparent to infrared. Example: silicon, germanium, gallium, and arsenic. Now another group of material compound is ceramics. Here atoms behave like either positive or negative ions and are bound by Coulomb forces between them. Example, glass, porcelain, and minerals. Minerals is also very, very difficult. I think Brown got the Nobel Prize, especially for categorization of the minerals. Brown got the Nobel Prize for this. He has 86 different types of classification of these minerals. So study of minerals is another challenge, and its classification is so very important. And Brown, one well-known scientist, got the Nobel Prize for classification and study of these minerals. Now, petroleum-based materials are, polymers. Polymers, we know, macromolecules formed by the union of large number of repeating monomer units in a regular fraction. We know the cellulose, starch, etc., where monomer is glucose or some other mannose or fructose. That type of monomers combined together in a linear fashion, especially containing carbon and hydrogen, and along with the other non-metals like nitrogen and sulfur. This vulcanized rubber and something like that containing sulfur. So polymers are macromolecules of associated with with some covalent bonds or non-covalent bonds involved in that. And of course, polymers are classified again synthetic and natural polymers. Synthetic polymers have a good mechanical and thermal properties, very strong, low weight, and inexpensive. And there are major advantages, especially to utilize these technological applications, as they are resistant, versatile, and all other inherent properties associated in these synthetic polymers. But we have limitations. Synthetic polymers, their biodegradability is a big problem. That is why we want to modify nowadays these synthetic polymers after introducing some new chemicals, just like pro-oxidants, as you know, hydrophobic nature converted into hydrophilic, so that these plastic material or polymer material may be consumed as a food by microorganism. Just like wood, this termite, they consumed as a food, because these type of microorganism, they containing this enzyme in their stomach, and they utilize these enzymes to digest these biopolymers. So especially this hydrophobic material is converted into hydrophilic material nowadays, friendly type materials, after introducing some new type chemicals. Now, another one is natural polymers. Of course, we have many advantages such as biocompatibility, biodegradability, non-toxicity, absorption properties, film forming ability, bioadhesion, hydrophilic nature, and in some cases, if you take this cellulose, they have some cationic, anionic properties in nature. So we may directly use it as a cation or anionic to capture some other chemical species from the environment or any samples. Now, the most important thing is sustainable development through the use of environment-friendly material has become one of the hottest topic of research all over the world. Different kinds of biopolymers can be used for different applications because of each material having its own inherent properties, especially for biomedical applications, food packing, food production and medicine, polymer composite, electrolyte for energy storage in supercapacitors, adhesives, cosmetic industries and textile industries, and of course material nowadays as an alternating energy sources, that also we want to include in this. Biopolymers such as cellulose, starch, agar, chitin and chitosan, and that type of macromolecules, biopolymers can be used for various day-to-day life applications in our this plant. Now, so I want to fabricate. I want to present two materials available from the nature, especially plant material and this marine species skeleton, like squid, crab and prawns. Their shelf can be utilized utilized for manufacture of this chitin and chitosan and some modification thereafter. So today we have present the material coming from two natural materials, one from cellulose and other one is chitosan. So I just want to share one or two slides, two material, of course hundreds of materials that we have, only want to introduce 2-3 materials from cellulose, especially for my biomedical application. Yeah, I have a small introduction regarding this cellulose, because cellulose is a natural material, so it's a very abundant, fast natural abundant material. So just I want to introduce. Cellulose was discovered in 1938 by French chemist Anselm Payen. I want to salute him because who isolated it from plants and determined its structural chemical formula as C6H10O5N. Now, the polymeric structure of cellulose was first introduced by Hermann Staudinger in 1920. And you remember this annual production of cellulose is estimated to be 10 raised to 11 to 10 raised to 12 ton per annum. So easily available with no cost, anybody can collect this type of materials from the nature without any cost. And this is the one advantage of this cellulose. Now, of course, Mother Nature creation, Mother Nature gift. So cellulose can be derived from various sources like plants. We have our cotton, etc. Bacteria is also another source, and a very high efficient cellulose nowadays is prepared from bacteria, a living organism. Then we have similarly animals, tunicates. Then algae is also utilized to extract cellulose from these for various applications. Because of these sources are very important, and different types of cellulose is obtained from these resources. That is why we utilize different sources, especially for different applications. So, of course, cellulose is being rigid, highly crystalline, and insoluble in common organic solvent is an ideal. That is why utilized as a structural engineering material. The ratio of amorphous cellulose to crystalline cellulose is called degree of crystallinity. It's very important, especially for chemist people to utilize this. Once you know the degree of crystallinity, then only what type of modification we need to convert a value-added product. So, of course, when you run this cellulose into an X-ray spectrophotometer, we have two different types of peaks, sharp peak and diffusive peak. Sharp peak, of course, coming from crystalline phase, and diffusive peak is coming from amorphous phase. That itself indicate that cellulose is having both amorphous and crystalline phase. Of course, chemist people utilize sometimes amorphous phase after converting this crystalline phase, or some other people for a particular application they want to eliminate crystalline phase and concentrate on amorphous phase. So both phases can be utilized according to their desire or according to their applications and inclusion of these properties. And of course, you just see the other things. Degree of crystallinity is, this cellulose obtained from bacteria is associated with 75% crystallinity. And of course, we have cotton, where you have crystallinity is 40 to 45%. Then algae is also 93% crystallinity there. So what I have concluded, degree of crystallinity is a very important role in chemical functionalization of cellulose. Now, you see, the structure is also very important. Even non-chemists also consider this structure for modification of their value-added product. We have primary alcoholic OH group. Basically, this glucose unit is arranged in a linear fashion. You see, this is the glucose unit. So this glucose unit, inside you see we have two glucose where 180-degree flipping is there. So alcoholic primary OH group is after 180 degrees flipping, primary group is returned to that 180 degree, so that we have two glucose units together combined. And so nowadays glucose is not a monomer of this cellulose. Earlier, glucose is categorized as a monomer of this cellulose. But you see, these two glucose units, there is a flipping in 180-degree flipping is there. So two glucose units combined together to nowadays known as cellobiose. So cellobiose is actually monomer which utilize to form a macromolecular structure. And we have, of course, three different OH groups. And beyond that, here this is when you identify the hydroxyl group, we have different strands is there, different layers are there. Within the layer itself, we have a hydrogen bonding with OH and oxygen atom of neighboring OH group. So OH group and oxygen atom of same strand is also form a hydrogen bonding, and at the same time OH group of one glucose unit from the one strand hydrogen bond with glucose molecules are associated with oxygen in another strands. So in that way, we have different types of hydrogen bondings may be formed, and that is why this, of course, we have a strong hydrogen bonding exists in this glucose structure, sorry, cellulose structure. Now, what are the properties of this cellulose? Basics, native cellulose. Most cellulose structure can absorb large quantities of water and now categorized as a hydrophobic, but it is insoluble in water. Cellulose consists of crystalline and amorphous region. I have already mentioned. So crystalline domain is highly ordered and much more stable compared to other their amorphous counterparts. By treating with the strong acids, amorphous regions can be broken up, and your material is highly crystalline and nowadays known as nano crystalline cellulose. Nano cellulose is actually nano crystalline. So when cellulose is treated with a strong acid, your product is now nano crystalline cellulose, because that amorphous phase may be totally disappear from the that phase. So in that way, we have, anyway, what are the reaction sites for a chemist? We have 3 hydroxyl groups present in this cellulose, and position is 2, 3, and 6 position we have. You see, we have carbon 1 and carbon 4 of 2 neighboring glucose may be interact with the acetyl group. Either group is the acetyl group. So in this particular case, we have beta 1 for addition is there. Okay, bonding is there. So in that way, we have consider second 2 position, then 3 position and 6 position OH group. 2 and 3 positions are secondary alcoholic OH group, less reactive compared with the 6 position primary OH group. But as a chemist, this we make utilize any OH group, maybe primary OH group or alcoholic OH group, after protecting each reaction site, so that we have many different types of derivatives that can be prepared after making utilize of each OH group, after protecting the other OH group by a suitable masking agent or protecting reagents. And this is what chemists can do or prepare a large number of material from the same raw materials. Then advantages. Cellulose possesses several advantages such as ability to absorb moisture, high strength and durability, high thermal stability, good biocompatibility, low density, and good mechanical property. These are the inherent properties associated with the cellulose. Now, advantages, there are many applications with this. This slide show the various applications of this cellulose. These personal hygiene products are produced, then removal of pollutant, especially these organic, inorganic, heavy metals and pesticide, like that. Different types of pollutants. Our environment is totally degraded due to this industrial establishment. So industries directly inject their pollutants. It's a wide spectrum of chemicals, maybe inorganic, organic, and cations, anions, and dyes, and pesticides, and wide spectrum of chemicals may be directly injected into the water bodies, especially in river and seas and all this. So we want to remove this pollutant from industrial wastewater before discharge, and so we make utilize this cellulose and cellulose modified material with different functional group and ligands to remove the chemical pollutants, especially from industrial process industries. Now, water reservoir, we have utilized this for this construction of this type of structures. Then absorption properties we have. Then drug delivery system we have fabricated. Then scaffolds for engineering and medicines. Then wound dressings, and even chemical sensors that we have manufactured from slight modification of this cellulose. Nowadays, wound dressings and even artificial skin may be fabricated, especially burnt skin may be replaced with this artificial skin coming from this cellulose materials. Now, Of course, we have limitations also. That is why we need a chemical modifier. What are the drawbacks of this cellulose? Pure dimensional stability, pure solubility in common solvent, lack of antimicrobial properties, low binding capacity to protein, high hydrophilicity, then pure mechanical strength and lack of thermal. These are some of the inherent drawbacks associated with this cellulose, and that is why chemist people modify the basic material according to they introduce their new properties. To overcome such drawbacks, the controlled and physical and chemical modification may be available, and introducing a new functional group into cellulose molecules through chemical modification is one of the key ways of solving these challenges. So usually there are many methods to modify this basic cellulose, which remove the limitations of or disadvantages already existing this cellulose. What are the methods? Esterification, etherification, cross-linking, graft copolymerization are the recently developed methods to improve the existing property of this cellulose. So what is what process taking place in esterification? Cellulose is converted into cellulose nitrate after treating with in presence of nitric acid treatment in presence of sulfuric acid and phosphoric acid or acetic acid. These are very simple techniques to prepare estates of this cellulose for wide applications. And other important cellulose estates are cellulose acetate, propanate. So we make utilize two acids simultaneously, acetic acid and propionic acid. In another case, we have acetic acid and butyric acid. So your material, cellulose material may be categorized as a cellulose acetate butyrate. Now, esterification of cellulose with carboxylic acid, carboxymethyl cellulose we have. So, and other type of carboxylic acid also you can utilize. And one of the most important problems that we face during the preparation is the solubility of this cellulose. So we have utilize a variety of solvents such as N2O4, DMF, acetic acid, sulfuric acid. So combination of different types of solvents, of course, utilized to during the preparation of the materials. Of course, your product may be differ from different solvent may be affected during the preparation of your material, and properties may be changed. So you select accordingly the suitable solvent for solubilizing your cellulose, so that your product may be entirely different with different properties. And this is one of the important things that chemists consider. More recently, we have ionic liquid as a solvent, especially imidazolium, solanium ions, which make utilize as a solvent, cellulose solvent. Now, etherification. Similarly, we want to modify it, different types of ethers. I don't want to explain all this because my topic is entirely different, but still modification is there. Etherification, we have prepared different types of ethers after introducing acylation. Even you can make utilize different position. I have already mentioned there are 3 different types of OH group, 2, 3, 6 position. So you can protect either 1 or 2 or 3 2 OH group, and you conduct experiment with the 3rd OH group. You can protect a 3rd group, then you can make utilize 2 and 3 position. So what I have concluded, there are different varieties of your product may be obtained after protecting each OH group and proceed reaction with other OH groups. And of course, here we have also utilize different types of solvent for during the preparation of your ether materials. Now, graft copolymerization. This is my topic, and I have prepared a material through this graft copolymerization methods. Now, what are the graft copolymers? Very simple. You have seen this red backbone of this monomer linear chain associated with the monomer, and we have a branch with the different monomers, and you make utilize this backbone of this polymer to attach, to bind these other monomer groups, and this is what is processing known as grafting of this branching or these derivatives. You can make utilize different types of monomers to bind this backbone of this, and this type of material is actually categorized as graft copolymers. And of course, polymer material with valuable properties can be achieved by via graft copolymer. These are the advantages of this because we can modify this monomer type. Degree of polymerization may be vary. Polydispersity of the main chain can be changed. Then graft density can be another factor to control these properties, and distribution of graft also determine its properties. So make utilize these different factors to during the preparation of the graft copolymers. And of course, graft copolymerization onto cellulose carried out different methods: free radical polymerization, ionic or ring opening polymerization, living radical polymerization. Among these three different polymerization steps, we prefer this free radical polymerization because this free radical polymerization having its own advantages, A to Z advantages. Its ability to provide an unlimited number of copolymers you can identify. Then you can make utilize as a graft monomer, methacrylate, methyl acrylamide, styrene, butadiene, vinyl acetate. Just like vinyl, even N-vinyl pyrrolidone can be utilized as a monomer to graft this backbone of this chain. So its tolerance to water or other impurities, then its tolerance to wide range of functional group. You can introduce any functional group, even amino group, carboxylic group, sulfonyl group, acetyl group. Like this, many different types of ligands you can introduce in your cellulose after modification through this free radical. So once you make utilize this free radical radical polymerization, there is no restriction. You can make utilize any ligands to introduce this in your material. So and of course convenient, very convenient this to conduct this free radical polymerization. Then mild reaction conditions, wide temperature range under which you can proceed this, you can conduct these experiments. Then very simple, this what is free radical mechanism? So formation of free radical is a very important steps. So here Fenton reagent is usually used as a for preparation of these OH groups, radical group, during the manufacture of your macro radicals. Here we have Fe2 plus reactive with hydrogen peroxide. We have Fe3 and OH radicals. These OH radicals, OH negative radical is highly active. They abstract one hydrogen atom from the cellulose, and we have a macro radical, just like cellulose or dot. This macro radical is highly reactive to your monomer. I have already mentioned that monomer with vinyl monomers or any other monomers, wide range of monomers you can utilize: acrylamide, acrylic acid, and methacrylic acid, glyceryl methacrylate. That type, any type of monomers you can be grafted for this cellulose. So once again, I want to conclude like this. So first we prepare this OH group through this particular simple reaction, and this OH group is highly reactive, abstract one hydrogen atom from macromolecules, and we have a macro radical, highly reactive. It will easily react with monomer to form a graft copolymer. Okay. So we have a backbone here, cellulose, and graft is monomer like acrylamide, acrylic acid, etc., etc. So here also we have this homopolymer is also, of course, these are disadvantages of these methods, but still we have considered this free radical polymerization. Then another free radical formation is this peroxide disulfate. We have break down this S2O824 as SO4 negative. These S2O4 2 negative or SO4 negative after formation of this radical. These radicals may be again this reactive with cellulose, abstract one hydrogen atom, and we have a macro radicals like this. And this macro radical is highly reactive and reactive with the monomer to form a graft copolymers. Similarly, we have ceric ammonium nitrate is also used as an initiator, where this ceric ammonium nitrate reactive with directly cellulose, and we have a macro radicals, and that macro radicals react with monomer to form a graft copolymer. I want to stop here because there are different methods we have. And another initiator is also acetobis isobutyronate. It's a very important initiator because here also we want to prepare first a radical. This is a very important reagent which we make utilize for manufacturing hundreds and hundreds of material from this bis isobutylonitrile. Structure of isobutylonitrile is this one, very simple. And here, this after breaking this bond, here we have a radical CH3 and CNC dot. This radical is highly reactive. As earlier, abstract one hydrogen atom from glucose, and we have a macromolecules like this. And it will react with other reagents like epichlorohydrin. We have epoxide ring, and this epoxide ring break, and we have a OH group is alcoholic OH group is formed, and we have cellulose grafted epichlorine formed. And this again further react with polyethyl amine. We have introduced amino group. So NH2 group is amino group we have introduced, and it will react with cross-linking agent like methylene bismethylamide, and we have a very good structure. You see that structure with amino functional group. So we start with the cellulose only having primary and secondary alcoholic OH group, convert it into an amino group material associated with an amino group. And what is the advantages of this amino group? Amino group is this material is especially directly utilized to capture metal ions, because we have a donor nitrogen atom where coordinated with the metal ions. Even otherwise, you can treat it with the succinic anhydride. Your NH2 become a NH or COH, something like that. We can introduce a COH group, a sulfonyl group, and even treated with HCl, we have a quaternary salts. So what I have concluded from this particular material can be directly utilized to capture metal ion from the environment, and also converted into other cationic or anionic exchanges, these ion exchanges. So usually ion exchanges is basically prepared from this material having amino group, because amino group is converted into COH group or sulfonyl group after treating with succinic anhydride or that type of chemicals. And even simple treatment with this HCl, that will convert it into a NH3 plus Cl negative. So that Cl may be exchanging with your anions like arsenate, arsenate, chromate, tungstate, and that type of anionic oxyanions can be removed from the water sample by treating with this material with HCl. Simple treatment with HCl, it will convert it to a strong anion exchanger. So what I have concluded, these type of materials may be converted into strong or weak cation exchanger or anionic exchanger to capture different types of chemical species present in your different samples, especially water sample or even industrial wastewater. Now, I have, our cellulose, of course, we have different materials that we have, naturally available material. And the sawdust, this waste from sawmills, sawdust is waste, and tons and tons of sawdust is coming from sawmill industry, and dump into this coastal area of this river, coastal belt of this river, and it will leach tannin, lignin, hemicellulose, that type of toxic chemicals into the water body. So we want to utilize this industrial waste, this cellulose-based waste. So sawdust is of course a waste material containing cellulose, hemicellulose, pectin, lignin, tannin, etc. We have different types of chemicals. So we want to remove all these chemicals and we want to extract cellulose, ultra pure cellulose compared with the commercial cellulose. So we actually utilize our starting material as a sawdust for the preparation of cellulose after treating with sulfuric acid, sodium hydroxide, hydrogen peroxide, etc., etc. Then we have finally treated with sulfuric acid. I have already mentioned earlier, cellulose is converted into this nanocellulose after breaking this amorphous phase, because cellulose containing both amorphous and crystalline phase. So amorphous phase may be disappear after treating with 50% sulfuric acid. So your cellulose is totally crystalline nature, and further treatment with the iron, ferric chloride, ferrous sulfate, and you introduce this Fe3O4 as a magnetic type material. So you can introduce this iron oxide into the cavities of this nanocellulose. So your material become a magnetic material. You can utilize external magnetic field to move here and there, and you can do a lot of things after applying external magnetic field. So that is why we introduce these magnetic materials inside these cavities of this nanocellulose, and after that we have treated with methacrylic acid and vinyl sulfonic acid. And you see, what is the ultimate, we have final material structure is, you see, we have introduced COH group, SO3H group, like primary alcoholic OH, keto group, different types of fingers and hands that we have introduced in our original cellulose. And this can be utilized, this material can be utilized for wide variety of application, especially to capture these metal ions or any that type of cations and etc. So what I have concluded, even this material, I have prepared this material especially for capturing highly specific selectivity. Have introduced, this after introducing, I always remember this because this particular material having two different acid group, COH and SO3H, with a different pK value. So with the different pK value, you can ionize this, sulfonite resonance structure, carboxylate resonance structure. So in between these two different types of resonance structures, we can introduce a selectivity, especially for hemoglobin. We want to separate hemoglobin from other protein mixtures or something like that, myoglobin or HSA, HSA from HSA. So that we have introduced a selectivity after introducing these different types of functional group, especially make utilize two different pK value. pK value means SO3H is ionizes to SO3 negative and H positive. That type of ionization is especially occur in two different pH. So within these two different pH, we have a different resonance structures that will helpful to create a selectivity inside this material. And of course, this material can be utilized to capture hemoglobin even in presence of other proteins. So we can introduce a selectivity inside this material. This is one of the important application of this material that we have make utilize. Okay. Now, another type of application is a drug delivery system. This drug delivery system is actually we make utilize this material to deliver drugs, different types of drugs, especially anti-cancer, antibiotics, analgesic, and different types of drugs that we have introduced into the human body, especially targeted to delivery of these drugs in different organs, different organs, liver, kidney, and different. So in that way, for that purpose, we have make utilize this cellulose for the manufacture of this drug delivery system, especially after modification. And just remember this. Of course, there are different types of materials available for controlled drug delivery into the different organ, and lipid-based, polymer-based, and inorganic nanoparticles, magnetic particles, cell-based, and nucleic acid and peptide-based, and like these different types of materials that we have introduced. And one of the most important drug delivery system derived from polymer-based carrier is very highly advantageous, especially relatively preparation is easy. Then vast source of chemistries are available there. We can introduce different types of drugs, especially through covalent, non-covalent bonding, because we can leach out. The release of this drug is also should be possible in that particular medium. So we always prefer non-covalent bonding between drug and these materials. So everything is these type of properties can be coming from this polymer-based drug delivery system. Of course, now there are advantages also, and I want to show two different slides. So different material prepared from cellulose, very important cellulose, and published these papers in highly impact factor journals. And ciprofloxacin is a drug for treatment of bone and joint infections, diarrhea, then lower respiratory tract infection. There are different application make utilize this type of drugs for different treatments, for different disease treatment. Now I am interested in preparation of this material. So we start with this cellulose, and this is a cellulose. Cellulose treated with acid hydrolysis there, and followed by incorporation of your magnetic particles. We have a MNP means magnetic nanoparticle cellulose associated with OH group, and this is treated with glycerol methacrylate, and at a temperature 90 degree in presence of hydroquinone, and we have glyceryl methacrylate grafted magnetic nanocellulose. And again further react with HEMA hydroxyethyl methacrylate and methyl sulfonic acid, acrylamide sulfonic acid, okay, acrylamide sulfonic acid. So we have introduced these two different chemicals with the GMA. So we have finally we have obtained a composite hydrogels. You know, there are different cavities, you know, and with the functional group SO3H. So even we have a cavities along with the material having SO3H group, a keto group is there. We have NH2 group, amino group is there. So different types of reaction sites is associated with this material, which is helpful for non-covalently bind with this ciprofloxacin drug. So and of course we well characterized using this different sophisticated instrumental techniques like FTR, SEM, and all this. We have XPS and VSM and all this. Okay, now I don't want to show all this. So finally, you know, we come to this because I want to introduce another two materials. So I want to conclude after characterization and application of this material, we can utilize this material to deliver these ciprofloxacin drugs into different organs and for treatment. Now, next one is also similar to, we have introduced another material drug delivery system derived from cellulose. And here we have 5-fluorouracil. 5-fluorouracil is actually, you know, this cytotoxic agent which interfere with the nucleic acid synthesis and inhibit DNA synthesis. It is widely used in the treatment of variety of different types of cancers like stomach, colon, and lungs, and breast cancer. So we want to introduce this anti-tumor or anti-cancer drugs within the tumor site after non-covalently bonded with this particular cellulose material. Here we also used this cellulose, then GMA and ethylene diamine treatment, and we have introduced NH2 group in cellulose. Remember that cellulose is associated with only primary alcoholic OH group. We have introduced a new NH2 group here, and it will another step in which cyclodextrin react with succinic acid, succinic anhydride. We have introduced COH group in dextrin, cyclodextrin, and it will react with this original earlier material product, and we have a material with the COH group, and like this, you know, there are different hundreds and hundreds of OH group is alcoholic OH group, and COH group is associated with this particular material. And this material is of course utilized to bind non-covalently bind with this 5-fluorouracil. Okay, and we have well characterized with FTR, XRD, SEM, and you know other type of instrumental facilities. And finally we utilize this in vitro studies, especially, you know, this so we study cytotoxicity with cell lines of cancer cell lines, especially breast cancer cells and all this. So what I have concluded again, you know, we have derived another drug delivery system derived from cellulose. Now another material that I have prepared is Chitosan from chitin. You know, Chitosan is a natural polymer. Sir, how much time that you have allocated means remaining time, sir? How much? Sir? Hello, sir?
Hello, sir.
How much time that remaining, sir, for me? How much time again?
10 more minutes, sir.
How much? 10 minutes. I take two, three materials. Okay, then I want to finish this. So another material is Chitosan. Actually, Chitosan is a natural polymer, second abundant available material from nature, especially prepared from chitin. Chitin is the second most abundant polysaccharide in nature after cellulose. The main commercial source of chitins are the shell waste of shrimp, crab, lobster, and krill and squid. The annual biosynthesis of chitin has been estimated as 10⁻⁹ to 10⁻11 tons. So this material is also available easily with no cost. You can easily collect this Chitosan as a exoskeleton of this species like shrimp, crab, and krill and squids. Okay, so and chitin and chitosan are both prepared using common process illustrated as we have you remove that flesh and we have an exoskeleton of squid, shrimp, and crab, especially made up of calcium phosphate, something like that. And actually, first process is decalcification with dilute aqueous HCl. So you treat with the dilute aqueous solution of this shell decalcination process may be taking place, followed by aqueous sodium hydroxide treatment, where deprotonation may be proteins and other chemical species may be disappear from this skeleton, and finally we have treated with 0.5% potassium permanganate aqueous solution and oxalic acid to become a crystalline nature material. And this material is categorized as a chitosan. And we have a acetyl group. Chitosan is having acetyl group and primary alcoholic OH group, secondary alcoholic OH group. Just remember the structure of this chitin. So primary alcoholic OH group, secondary alcoholic OH group, and we have an acetyl group. So deacetylation, when you remove this acetyl group and convert it into an amino group, this group may be converted into an amino group, and that material is not categorized as a chitosan. So chitosan is actually a deacetylated product of chitin. So where you treated with this acid, treated with sodium hydroxide, so your acetyl group may be disappear and NHAC become NH2 group. So finally, I want to conclude like this. So chitosan, what are the reaction sites present in chitosan? Primary alcoholic OH group in 6th position, and we have amino group and less reactive secondary alcoholic OH group. So as a chemistry, we can utilize both primary OH group, secondary alcoholic OH group, NH2 group, etc., for introduce any other modification. After modification, introduce different types of functional group. And of course, now I want to prepare a large number of materials from these chitins, and you see one of the most important material which I have published this paper in polymer with applied polymer chemistry with high impact factor, maybe 9 point something impact factor nowadays, RSC advances, RSC publications. Now the material is 2-acrylamide, 2-methyl propane sulfonic acid grafted and belayl chitosan intercalated monomerate for controlled delivery of 5-fluoroacyl. This material is very simple, very simple. Once again, I come to this point. Now, this is a clay monomerate where you have a layer structure. We have silicate and silicate layers are there. So alumina octahedra and silica tetrahedra arranged in layers, and in between these layers we have a cavity associated with the sodium ions or calcium or potassium counter positive ions. So, and this is the despacing in between two layers, and we have a 12 Armstrong unit cavities there. So we make utilize these cavities in between these two layers, alumina or silica tetrahedra, alumina octahedra layers, and we have introduced this type of 2-acrylamide or 2-methyl propane sulfonic. What is this this material? N-mallyl chitosan. This is the N-mallyl chitosan. After you prepare this N-mallyl chitosan, after acetylation reactions, so that you can introduce COH group and introduce in a CH2OH. So what I have done is this primary alcoholic OH group is converted into an acrylic acid group, and we have NH2 retained there, and this mallyl chitosan is actually introduced into the cavities, interlayer structures of this monomerate. Then after that, we have introduced monomer and treated with initiator and cross-linking agent. So your product is become like this. And of course, this layer structure monomerate containing this chitosan derivatives having a COH group. And this COH group can be utilized for COH and SO3H group. Both the COH and SO3H group is present in this particular material, so that we can make utilize resonance structure to covalently bond with this 5-fluorouracil anti-cancer drugs. Now, and this is the mechanism, cytotoxic studies and all characterization is well characterized. And second, another material is, we can introduce doxorubicin as an anti-cancer drugs into this layer structure after treating with this carboxymethyl chitosan. So just remember this again. Chitosan is converted into carboxymethyl chitosan capped with magnetic nanoparticles, and this involved 2-3 steps. And after preparing this CMCS capped MNP, we have introduced this product inside the interlayer structure, interlayer cavities of these clay minerals. What is the importance of this material? I want to conclude like this. So this material demonstrated that carboxymethyl cellulose chitosan capped magnetic nanoparticle intercalated monomer is not only a good delivery system for doxorubicin, but also appear to be a promising strategy for protecting against oxidative injury observed, especially when we make utilize this doxorubicin induced cardiotoxicity. So actually, when you use this doxorubicin, there is a side effect. Cardiotoxicity is there, so we want to introduce this reactive oxygen to capture repair this damaged phenomena, especially in this cardiotoxicity. So there are two advantages, especially for introducing this doxorubicin, and doxorubicin having side effect. That side effect may be eliminated after introducing this new material. This is the advantages of this material, and this material is also published. This article, this finding is also published in a very good journal. Okay, because this side effect is also we can eliminate after using this type of materials. Okay, now multiple drug. This is another advantage of this material, chitosan materials. So what happens when we have introduced only one drugs at a time. But if you make utilize these antibiotics, and sometimes we make utilize material to introduce simultaneously 2 drugs. One may be antibiotics, and another one may be analgesic. Especially during the surgery, we provide analgesic to as a painkiller to reduce the pain during surgery. So simultaneously we make utilize introducing 2 different drugs. Maybe combination may be there, cancer anti-cancer drug associated with antibiotics or analgesic or something. So some combination may be there. So once you identify the combination of 2 drugs and you introduce 2 drugs simultaneously into human body or in different organs, so that we make utilize this chitosan to prepare a very complicated drug delivery system, which make utilize to deliver simultaneously 2 different types of drugs. One drug may be hydrophobic, other drug may be hydrophilic. So what I have concluded, your drug delivery system, your material should have 2 different phases. One is core associated with hydrophobic. You can introduce this hydrophobic drug into hydrophobic phase and coated with your hydrophilic phase in which where you can accommodate hydrophilic drug. So if you want to introduce 2 different drugs with different properties into a particular drug carrier system, so your drug carrier system also associated with the 2 different phases. So fabrication of this type of material is very, very, very difficult because of the complexity to introduce these 2 different phases, especially core and enveloped with another type of polymer network. So just you see this, I want to stop here after introducing this. So here also we have chitosan treated with acetic acid, and we have some modification with olewic acid, and just you see here we have a hydrophobic core. Have you seen this hydrophobic core, and we have a hydrophilic end. This is just like a micelle where you have a hydrophobic core is formed, and here you can accommodate hydrophobic drug, maybe curcumin. Curcumin may be hydrophobic drug used for anti-cancer, something like that. Okay, so you can create a hydrophobic core inside the material, and outer side you see a hydrophilic nature. And similarly, you can create another phase. So you can introduce by this drug one, this is hydrophobic drug. Inside this hydrophobic core, where we have a hydrophilic end, and so that what happens? This will again. So after introducing your first drug inside this cavity, and further treatment with the polyvinyl alcohol and polyethylene glycol, you see we have another network. Just like this, we have a envelope like hydrophilic polymers like this. So what is its advantages? We have introduced another hydrophilic drugs. So we have both hydrophobic drugs and hydrophilic drugs. And once at a particular pH, especially at a 7.4, the best release of hydrophilic drug is coming from this material, followed by slow release of your hydrophobic drugs. So first we need hydrophilic drugs, especially if take it example hydrophilic drug painkiller. After immediate surgery, we need immediate release of hydrophilic drugs. So you can introduce this hydrophilic drug outside of this material. So just I want to conclude. So what is the importance of this material is we can introduce this two different phases, hydrophobic core and hydrophilic network, where your two drugs may be having different properties, may be associated in different application. Okay. Now I want to move another important material that we have. This glaucoma treatment. We have glaucoma treatment is eye drops or cream that we have introduced in eye. And we have injection. Sometimes drug may be introduced in your eye through injection, and we have a contact lens. So my work is also associated with the contact lens. So just I want to introduce. We have prepared a large number of contact lens from Chitosan after very complicated modifications that we have adopted. And of course, our material, our contact lens is very cheap, and we can utilize 3 or 4 times without losing efficiency of this material. Because why I introduced this material, commercial available contact lens may be very costly, and even a single dose you can introduce after 30 days. Just to remember, my dear colleagues, after 30 days only commercial available contact lens can be utilized. So just like a throw and use and throw mechanism, that type of materials that we have available in commercially available. So very costly, and so we want to replace these costly materials. And even you can wait 30 days to introduce your a single dose of your anti-glaucoma drug, especially thymol malate, that type of drugs that we have. Thymol malate drug is anti-glaucoma drug. So our idea is to fabricate a very cheap material available to market, and repeatedly you can replace. At a time you can need 2 lens. Even a night after using daytime, you can replace that lens, and you keep it in a vessel containing your drug. During night time, the drug may be diffuses and penetrate into these cavities of this lens, and you can utilize this lens in next day to release these drugs in your eye, so that you can make utilize 1 or 2 contact lenses simultaneously, so that you can even with after spending 3 days, you can introduce your required drugs into the eyes for treating this glaucoma. So what is the this type of lens is known as therapeutic contact lens. So therapeutic contact lens means contact lens plus drug. So drug is introduced into this lens, and your lens is categorized as a therapeutic contact lens. So recent report on therapeutic contact lens utilizes 30 days for releasing a single dosage of this anti-glaucoma drugs TML. So we have prepared. Our idea is to prepare a very cheap contact lens from Chitosan. So material is very Chitosan, then hydroxyethyl methacrylate. Just remember, these chemicals are very cheap. So Chitosan, hydroxyethyl methacrylate, then your drug is thymolol malate, and these are the material you especially make utilize. So, we make utilize a new technology, molecular imprinting technology, to fabricate this therapeutic contact lens. What is molecular imprinting technology? Just I want to introduce within a few seconds. You know, we have different types of monomers. You know, these green, red, and blue. These are these different types of monomers. In presence of your template. Template is, you know, take it as a drug or something like that. So target molecules. And you know, we have a self-assembly. We have create environment so that these monomers, different types of monomers, combined together with these target molecules and polymerizes together. And you see, this is our polymer network. And you know, your template, your drug may be inside this cavity. And once you remove this drug with a suitable solvent, so extraction of this template molecule with the solvent, you can create a shadow, you can create an image inside this cavity. And these cavities only can be utilized to accommodate this template, earlier template. So what is we can create a cavity or an image inside this polymer network. So that you can accommodate this specific drug. So this is what selectivity comes. How the selectivity comes. So just you remember once again, there are different types of monomer that we have selected, and in presence of target molecules, we have provided a suitable environment so that reaction conditions, so that we have a polymerized material network is formed, and with find out your suitable solvent to extract this drug. And this is the method that we have introduced. Our fabrication of contact lens, and this technology is known as molecular imprinting polymer. Now you see, of course, there are different types of mechanism that we have involved: non-covalent molecular imprinting, then covalent molecular imprinting, and we have a metal coordinating molecular imprinting. What is the advantages of one over the other one? Usually, chemist people utilize non-covalent imprinting. I have already mentioned earlier, we have a monomer and template, and we have a polymer network like this. And here, this template and monomers are interact with the non-covalent bond. This is just like hydrogen bonding, weak van der Waals forces, so that you can utilize any solvent, suitable solvent, to break this, to leach out this template molecules, maybe drug or pesticide or any other chemical species which interact with this monomer reaction sites through hydrogen bonding mechanism, non-covalent bonding. Now next you see another, so covalent imprinting is also there. We have a covalent bond, strong bonding with this template molecules and monomers inside this polymer network. So it is very difficult to break this, to leach out this covalently bond templates. So we prefer this non-covalent bonding, and we have prepared manufacture a therapeutic contact lens from Chitosan. So just you see one or two steps. We have utilize Chitosan, acetylation, acetyl Chitosan, then treated with chloroacetic acid and sodium hydroxide, and these are the different various steps that we want to prepare, and we have introduced hydroxyethyl methacrylate, and another step treated with acrylamide, and we have a polymer network. Just to remember this, we have this is a and this template, this template is a drug thymolol malate is this is the drug that we have introduced in this cavity, and we have create an image. We have a cavity image. You see here we have a drug. So, and this is a reversible process. When you introduce again after leaching out your drug, and we have introduced a cavity. Whenever you introduce this your material after leach out of this template in a solvent containing your drug, of course that drug is highly selective, and even in presence of other chemicals, your drug is only accommodated inside this cavity, because we want to introduce a cavity or image for that particular highly selective template molecule. So just to remember, my dear colleagues, okay? So, and this is a contact lens that we have prepared and highly efficient, and we have well characterized with different instrumental techniques and, you know, dynamic mechanical analysis. And this is our lens that we have introduced this. Yeah. Okay. Now you see. This is our lens that we have introduced commercially. We want to introduce in future. So, and most of the properties that we have studied, and we have a good publication for this material. Bioconjugate chemistry, I remember this publication. Okay. Now we move to the next, some studies and all this. Okay. Now, and there are many other properties that we have introduced. Okay. Then. Sir, one minute, sir. We have here also, we have introduced a combination chemotherapy. Just without any slides, I just take another 30 seconds, sir. So we have also prepared a material which can accommodate 2 anti-cancer drugs. Here we have utilize anti-cancer drugs, curcumin and 5-fluoro. What is the importance of curcumin? Curcumin is especially, you know, treated for neck cancer, and 5-fluorouracil is treated for skin cancer. So our idea is to prepare a drug delivery system for introducing 2 different anti-cancer drugs. Here also we have, one is hydrophobic and other one is hydrophilic, and you know, these 2 anti-cancer drugs may be introduced in a particular material. And see, just we see here, this slide is sufficient to explain this mechanism. You see, this is a chitosan coated curcumin loaded aminated beta cyclodextrin molecule, and this is one material, and another material that we have prepared for accommodating 5-fluorouracil. Just remember once again, we have prepared a material with a different functional group, and we have a core. Inside this core, we have introduced curcumin, drug treated for anti-cancer for neck cancer. Okay. Then this is a 5-fluorouracil, another anti-cancer drug, especially for treating skin cancer. So we have these 2 material accommodate to 2 different anti-cancer drugs, and these 2 material is dispersed in polyhydroxyethyl methacrylate film. This is actually, you can categorize as a film. You know, this is a film. Inside this film, we have introduced these 2 different material paste. You know, just like a patch. You can utilize this patch, and you can introduce 2 different solvents. One is butanol, and here we utilize 2 solvent. One is butanol, and the other one is ethanol. So the mechanism is, once you utilize this patch, and you introduce these 2 different solvent, what happens? This one of the solvent may be highly selective for one particular drug from the core. You know, here what happens? Curcumin is coming from after treatment with butanol, but a small amount of 5-fluorouracil is also coming. And in other cases, all these solvent may be less toxic. Ethanol is another solvent which can be utilized to release our 5-fluorouracil. At that time also, we have a small amount of curcumin is also coming. Now what I have concluded, because we have no time, there are other slides also. We have fabricate different types of material, especially, you know, this patches, artificial, just like artificial patches to accommodate different types of materials which containing different types of drugs, so that even here we have utilize 2 different solvent to leach out 2 different drugs in 2 different conditions. Okay. But if you go through other slides, there are a large number of slides I have. But if you go through another material, you know, this material, when accommodated 2 different drugs simultaneously release, even after applying external magnetic field or external, you know, ultrasound. So even recently we have published different material which accommodate different types of drugs, and just application of external, you know, even temperature even ultrasound, with a particular frequency. With this frequency, some vibration within this vibrational frequency, or that particular frequency, sufficient to leach out different types of drugs from different material. And these different types of material that we have introduced, and we have more than 100 slides I have written there, and I have no time to explain all this. So my idea is to introduce a new material, especially from naturally available material like Chitosan, or cellulose, or that type of organic acid, and that type of natural material, because eco-friendly material and less toxic, biocompatible and biodegradable. When after utilization of this material, you can directly dump into this environment, so that within a few days it will degrade. We have already conducted biodegradable studies. When it contact with after utilization, all this material, when contact with soil containing microorganism, may be degraded. They take it as a food material for degrading all this material. Thank you for listening my talk, and wish you all the best. Okay, thank you, sir.